Okay. Thank you very much for inviting me to your special occasion on the 20th anniversary of Peking University Graduate School in Shenzhen. I'm also very pleased to be here because I am one of the first honorary professors of Peking University Shenzhen Graduate School. So thank you for honoring me twice, first making me an honorary professor, and then inviting me to speak to you as an electrical engineer. The title of my talk is Solar PV, the core technology to balance the planet. So solar PV we all know about. It's become a mature technology, but it's actually going to be a key technology for us in terms of humanity. And I hope I'll show you why. So the source of all energy on our planet is the sun. The sun is an uncontrolled nuclear fusion reactor very far away, 1.5 10 to the 18 kilometers away. And then it radiates energy, and our planet captures some of that energy. The energy captured is, the radiation per day is 343 watts per meter squared. And that comes in, some of it gets bounced off by the Earth's atmosphere. About 240 watts per meter squared reaches the Earth's surface. Some of that gets reflected off the surface. Some of that is absorbed, and then it's re-radiated back out. And the important thing for our planet is that this energy coming in to the energy going out has to be balanced. If it's not balanced, the planet will heat up. Okay, now there's a misnomer that this is called the greenhouse effect. Okay, but this is not a greenhouse problem. This is a re-radiation issue. And what happens is there are some gases which absorb some of this radiated energy and re-radiate it back to the Earth, and the Earth has to then radiate it back out again. So this is not really the greenhouse effect at all. What it is a reduction in radiation efficiency. Just to make the point, this is the incoming radiation in the visible. Some of it is absorbed in the atmosphere by ozone. These are the gases, atmospheric gases, which there. Some of it reaches the Earth. Of course, the ozone is important to take away the UV, otherwise we'll all get burnt up. The Earth absorbs it, and then it re-radiates, but it re-radiates in the infrared. Okay, so this is coming in the hundreds of nanometer and be re-radiated in the infrared zone. Some of this radiation is absorbed by atmospheric gas or gases and re-radiates out in both ways. Some of it goes out and some of it comes back to the Earth. Now, in order to keep the radiation balance, it's Stefan's law. Okay, to keep the balance, to have the same radiated energy, if the radiation efficiency is less, the temperature rises. That means there's a slight shift in the infrared band towards this way. It heats up and balance is kept. So the issue is, in keeping this radiation balance, if the radiation efficiency goes down, then the temperature will go up. Okay, so that's the CO2 argument. And to note that CO2, the Earth has a CO2 atmosphere, all plants emit CO2, and our activity, man-made activity, accounts for less than 5% of the global CO2. But why is there such concern about it? Well, maybe the response of the planet is nonlinear. Okay, so if we look at this, if we look at the CO2 has been measured since 1960 in Mauna Loa in Hawaii, and that's that CO2, atmospheric CO2, has been measured. There's a annual cycle between the summer and the winter. More CO2 when in the northern hemisphere the trees don't have leaves, but the trend has been that it's gone up, and this is parts per million. We then have the temperature global temperature. And the global temperature has been, oscillating about industrial age. It was cool. And right up to about 60s, it was sort of not clear that there was a temperature rise. But since 1980 or so, there's been this rise in temperature, okay? So there's a rise in CO2 and there's a rise in temperature. Is there a correlation? Is it causal? Is this temperature rise due to the CO2 rise? It can't be, we don't know for sure, but all the modeling that we have, it's a very difficult thing to model the Earth's atmosphere, as you know, to predict the weather in a year's time is going to be, difficult. But nevertheless, all the modeling seems to suggest that there is a causal link between this CO2 rise and this temperature rise. And based on the modeling and our knowledge, it's not an option not to do anything and wait. So the idea is that we are going to try and reduce the CO2 on the modeling assumption, modeling data saying that these two things are correlated. And this is, of course, the rise that stopped in 2010, the previous data. You can see it's kept rising, okay? So that's a concern of CO2. There's a correlation with warming. But there's actually a much better reason or important reason to reduce CO2 in our atmosphere. And that's because of the ocean and the ocean acidification. The sink of CO2 on our planet is the sea. And in sinking CO2, the process of doing so requires the creation of this carbonic acid. Okay, carbonic acid is short-lived, but it's important in the process by which CO2 is sunk in the water, and it's constantly created and degraded. But this carbonic acid acidifies the ocean, and this shows the pH rise, the reduction in pH, which means that it's becoming acidic. Now, this is a log scale. So a 0.1 reduction in pH is a 26% rise in acidity. Okay? So this data we've had, we know that the oceans are acidifying. If the oceans are acidifying, the whole ecological balance of our planet comes into question. So in balancing the planet, it's a good idea for us to try and reduce CO2 based on human activity. Okay, so let's assume that is, that's a good thing to do. And there are good reasons to do that in terms of balancing our planet. Now, in reducing CO2, the issue is, do we need to take the stored solar energy? That is, the stored solar energy is mineral oils. That is energy from plants, which is degraded over many hundreds of years and has been stored as chemical energy. If we release that stored energy, we release CO2. Instead of doing that, is there a possibility for us to take the energy which is being radiated from our star onto our planet, and this gives us the resource, the outer box. The inner box, the orange box, is what it is. I keep pressing the wrong one, sorry. Sorry for that. So this is the resource on the Earth, the wind energy base, which is also due to solar and creating pressure differences in the Earth's atmosphere. And the human energy use is the small blue box. So there's plenty of solar resource coming, and it should not be beyond our capability in the 21st century to try and meet our energy needs from the energy which is being radiated by the sun onto the planet in real time, rather than having it stored through minerals or digging up the historic stored energy. Okay. So in collecting solar energy, you can do it thermally, but all biological processes, food, photosynthesis is basically capturing energy all the time, obviously, right? So here we are going to talk about photovoltaics. And the photovoltaics is it's an electronic device where you capture, all of you would know that you capture the sun, you create electrons and holes in a p-n junction, and you can get electricity. So, but since this is an electrical engineering talk, I mean, we should really review this. So incoming photon flux, okay, has an energy of HF, the packet of energy, which is a photon, which I've put it in a little packet. If that has energy larger than the energy gap, obviously, you create an electron-hole pair. Okay, so the creating of the electron-hole pairs, you have to create, you excite the electron, as you would know from your lectures, but you have to create this virtual particle, which is a hole. All right, so absorption of a photon, this is fundamental, requires the creation of two particles. That is a negative particle and a positive particle. According to quantum electrodynamics, photons are always decaying into electrons and positrons and recombining again to make photons. But this process we do in a solid, and the absorption of a photon can only be done in a solid efficiently because of the creation of this virtual particle, which we call the hole. So it's quite very important. So, okay, so that's the first thing we do. We absorb, we create electron-hole pairs, and then we have to separate them. Okay, so the p-n junction, p-doped, n-doped, as you know, you get a potential at the interface, the metallurgical interface between the p and n region, and that allows us to have a field to separate the charge, and that is essentially the photovoltaic effect, okay? Photons in, a voltage out. That, oops, I'm not sure. Okay, that doesn't matter. Okay, so that's the photovoltaic effect. And, that's, you can draw power out of this, obviously. I did have something there, but it's not. So this is where I left off. So if we were to draw a current, obviously, from the, well, let's see. So the open circuit voltage, I'm not sure where that is. Okay, doesn't matter. Okay, as you can see, the open circuit voltage is at the bottom there, VOC, and if you try to draw a current, the ultimate current you can draw is the short circuit current, right? So I'm not sure what's happened to the pointer, but does this have a pointer? Okay. No, that won't seem. No, I want this pointer. Not working? Okay, all right, doesn't matter. So the ISC, the short circuit current, obviously, is related directly to the photon flux. Okay, so from the solar spectrum, you can only gather the energy which is larger than the band gap. So if you take silicon, that means that it's roughly about 40% of the photon flux from the sun can be captured by a silicon semiconductor, okay? So that will work out to be something like 40 milliamps per centimeter squared, the short circuit current. And remember that the quantum efficiency is the photon, current, the short circuit current divided by the photon flux, right? That's the quantum efficiency. And that can be very high. That can be 70, 80, 90% even. But that's not power efficiency. Because the power efficiency is that to get power, you also need a voltage, and you need to draw it out at some voltage. So VOC for a silicon PN junction is maximum is 0.7. It's somewhere below that by the time you draw current. So the maximum efficiency that you can get from a silicon solar cell is 0.7 times 40. That is about 28 milliwatts per centimeter squared. And the sun's at AM 1.5, the power is 100 milliwatts per centimeter squared. So the maximum efficiency we can expect out of a silicon solar cell is about 26%, 27 to 26%. Okay, that's the maximum single junction solar cell can achieve, okay, in giving power. So remember that number, 26 to 27%, okay? Now, So let's say we can generate solar electricity. So that is just the very basic idea of how we convert photons or sunlight into electricity. So now what do we need to think about? When we generate electricity, the important thing to remember is that it's a prerequisite for economic growth and improving in living standards. 80% of the global energy is consumed by 30% of the global population of 7 billion people. It's very unbalanced in that sense. There are 2 billion people in the world who are not connected to the conventional supply grid at all. And as the global economy and population expands, there will be a huge demand for energy. So it's not what we have now. We need to think about a rapid growth in the demand as well, okay? And the limited high voltage, expansion of the high voltage grid, as was done in the 19th century and the 20th century into the 21st century, is also becoming unviable because of land concerns and cost concerns. So energy demand is directly proportionally related to population growth. As the population grows, our energy demand grows. And if you look at the projection, it's a 28% growth in energy demand between 2015 and 2040. And you can see that most of that demand will be in the non-OECD countries, obviously because these are the countries which are developing and catching up. Of those, mainly in Asia because of India and China. And that's where the demand will be for the growth in energy. Now, this is an important thing. I don't have the pointer to do this properly, but do you have a mic? Give me the mic, then I can actually go there. That's easier. Oh, okay, so you can see this graph, population, growth in population in non-OECD countries, also OECD, per capita gross domestic product in thousands of dollars. That is the economic output from the non-OECD countries and the OECD countries. So this side of the graph is going up, okay? So population goes up, economic productivity goes up. So how are we going to balance the CO2? How are we going to have more people, more production, and somehow balance the CO2 requirement? Well, that's based on the projection that for every 1,000 BTU per dollar, that's the energy required to produce $1 of output, will keep coming down, okay? So the red line comes down faster in the non-OECD countries because we will adopt newer technologies compared to the more mature economies. But you can see the more mature economies are also growing in terms of output, right, from a high point. And we are assuming that the carbon intensity for the energy intensity, the carbon output will also go down. So somehow we think that the downward trend on the right side will balance the upward trend on the left-hand side. Okay, so this is at best an assumption. And I think for the students here in your working life, the challenge will be, can we actually make this sustainable? Can we balance this even if it becomes carbon neutral? Okay, so that's a challenge, I think, which we will face. So if you look at solar PV and its capacity, it's at the moment, it's about 700 gigawatts peak. Last year, even though there was a pandemic, there was 120 gigawatts installed peak. It's peak, of course. Just to give you some idea, a nuclear power plant is a 2.2 gigawatt output. Okay, so even if you take the peak and reduce it, it's still a significant capacity. It's only 3% of the global demand at the moment, but you can see that the growth is non-linear. And the important thing to note is that there is energy embodied in making photovoltaics, okay? So if we were to look at the energy recovery from a photovoltaic panel, it has to generate for 2 years to recover the energy that went into manufacturing it. Okay, so if you look at the 100 gigawatts which was installed, in the last year, immediately, you had to pull back 2 years to say, you know what? It really means that in the existing capacity, that amount, 240 gigawatts, has already been expended in the new installation. And if we went to the next year, so the year before, already it has generated for 1 year, it's come down to that point. But what I want to emphasize is around 300 gigawatts of the solar output is completely contributing to reducing CO2, even as we put in more solar. So we've crossed the threshold where solar installation is actually costing more than it's generating. That has been crossed, and now we are in a positive feedback cycle. The more solar you put, the more CO2 you will reduce. So that's an important point to emphasize. So the world's biggest solar plant at the moment is in India. This keeps changing. It's 2.25 gigawatts over 4,500 hectares. But of course, in China, there's one which is almost the same, 2.2 gigawatts over 5,000 hectares, which is in Qinghai on the Tibetan plain. But on the left-hand side, you can see there's another solar hydro project of 0.8 gigawatts in Longyangsha. Okay, so I think the important point to make is that photovoltaics is very much right now a Chinese industry. It is being adopted rapidly in China, and it's a contribution that China is making to the entire world. All those Indian panels have come from China. Okay, so the cost effectiveness of manufacturing solar photovoltaics is a great contribution that China is making. It's one of your industries to the balancing of the planet through photovoltaics. Okay, but in its use, photovoltaics has another important point, that it can be the only source of power generation which can be done in an urban environment without pollution. Okay? So in Europe, there's a lot of experience in building photovoltaics as part of the urban landscape. This is integration of photovoltaics into housing. That's called building integrated. This goes back 20 to 25 years in Europe, started in Germany, in England as well. And this is in England, where outside the buildings are photovoltaic. So these are all urban power plants. This is a housing estate again, which can balance its requirements by photovoltaic generation in eco housing. And now it's more than balancing, it's energy credit. Since about 2010, that's possible. And this is in Munich. This goes back 25 years. The Munich exhibition plant. This is an urban power generating plant, which is photovoltaic. So photovoltaics for urban generation is possible. It's been demonstrated. And I think it's also in urban centers, urban heavy environments such as China, hopefully you will see more urban power generation, which happens, which means you don't have to build big power lines across the country. And in transport, it's very interesting that there's an annual race which takes place in the solar car race in Australia from Darwin to Adelaide. It's 3,000 kilometers. And normally you get single-seater photovoltaic driven cars like so. This is a university competition and different universities enter cars. But importantly, in 2018, instead of a single seater, the Technical University of Eindhoven entered a 5-seater car. The 5 passengers on an average speed of is entirely powered by onboard solar and batteries. Okay, and this could be hailed as an indicator for future transport. Of course, it's light. The way to look at this is not like a conventional car, but it's more like a multi-seater bicycle. very light body, urban transport, and it can still be green. Yeah. This one, yeah. This one here, right? Okay. Thank you. Display. Okay. All right. So that's, I'm sorry about the technical hitches, but anyway, so for urban transport, photovoltaics has also a role to play, but it's be a new type of transport, right? It won't be the traditional electric vehicle you see, which looks like an SUV. It's more like your electric bicycle, but expanded to 5 people. Now, this adoption of photovoltaics is very important because the price has reduced by 99.6% in 1976. So what was an unviable technology and a curiosity back in the 1970s has now reduced to the point where it's for $1, under $1, it's under $1 per watt. It's about 20 cents. But the right hand is actually more important because it is showing the levelized cost of electricity. That is, if you build a power plant, the amount of capital you have to put into the power plant plus its operational cost. On the levelized cost of electricity, you can see that solar since 2010 to 2019 has dropped by 89% to the point now it is the cheapest levelized cost of electricity to install. And this is in megawatt hours. Okay, so this is electricity generated, not peak capacity. This is actual projection of megawatt hours. The cheapest technology to install right now is solar. It crossed wind, onshore wind. And so therefore, the adoption of photovoltaics is being driven mainly because of this. It is the cheapest power generating technology to implement. And that is why we're likely to see an exponential growth in this technology because of the reduction in cost or the efficiency of or the power that can be generated. Now you can see around about 2005, 2015, the price dropped dramatically. And that's because the efficiency of solar cells also went up in terms of their adoption. It's crystalline silicon rather than multicrystalline. And it has this cell called the PERC cell. Okay, this is, again, a costing I won't go into because we're running out of time. So this is a highly engineered product now, right? So this is anti-reflection coating. This is the N+ emitter at the top, PN junction. There is a lot of materials which has been done, material science to passivate the surface so that you don't get recombination. It's been highly engineered. This is the P+, is not now uniform. The P+ is in islands and it's contacted. Now, these types of cell, which is called the PERC cell, which the idea originates from the University of New South Wales and Martin Green, was too expensive to be adopted until about 2015. But now all panels essentially are bigger, 8-inch silicon, and they're operating at about 22% efficiency. And so this is the inverse when you can also have what you call a bifacial solar cell. That is, the light enters not only from the front, it can also enter from the back. You can see the metallization is broken, and you have a rear grid contact, and the light can enter from the back. Why is that? Well, it's because you can have now capture of diffuse light off the surface at the back. So this enhances the energy yield from photovoltaics very significantly, even though the efficiency of the silicon solar cell in conversion of the direct sunlight is about 22%, it can capture more light through diffuse and reflected light at the back. Okay, and this is from a solar cell, as you can see, up to 25% increase in the harvested energy. This is from a Chinese company, one of the biggest companies, Trina Solar. And you can see the rating is 485 watts right at the extreme, but under bifacial conditions, that can go up to 606 watts in terms of the energy that can be generated. So these are very interesting engineering which has gone in over the years to maximize the output of photovoltaics. Right now, remember the number I gave you was 27 to 28% efficiency. The highest efficiency from a solar cell right now is 25.6%, and this comes from a tunnel oxide passivated contact design. What does that mean? It means that there's been passivation. Sorry. Okay, the back contact is silver, but it's a polysilicon N-type. This is silicon, but there's a tunnel oxide here, which passivates the silicon with this back contact ideally. Okay, that tunnel oxide, if you look at that, this is a 6 nanometer scale, is about 2 to 3 nanometers, which is engineered over an 8-inch wafer. Okay, and there it relies on a tunneling so that the barrier is such that the electrons actually tunnel through this passivation barrier. So the silicon is completely passivated at the back. It's passivated at the top as well. And you are pulling the efficiency up to about 25.6%. Almost within 1% of what can be achieved ideally and theoretically. And I think the engineering is very interesting that you have a tunnel oxide in a silicon solar cell, which is over 8 inches. Okay, and that tunnel oxide has to be controlled very well to 2 to 3 nanometers. Yeah, so that's a tunneling idea. And then you can have the bifacial version of that as well. Okay, so you can have the singles version, but you can have the bifacial version, which allows solar to come from the back. And that just went into production or was announced last month by Jinko Solar, which is a Chinese company, maybe the second largest manufacturer. And they're the first people to take in this TOPCon wafers into production. Okay, you can see the efficiency of the panel. At the panel level is 22.3%. At the device level, it's about 25, 26%. There's a degradation, obviously. But everything is not 100%. And I think this is what I would like to say. This is an article from Der Spiegel, the German magazine, and there's a growing awareness that what we call clean technologies are not perhaps that clean. Why is that? If you take a wind turbine, what do you think about a wind turbine? Well, a wind turbine has around 67 tons of copper in it for the generator and its conversion. To put 67 tons of copper into a 2 megawatt generator, one has to dig 50,000 tons of ore in Chile or some other place, okay? So the problem is that even if our technology is non-CO2 emitting, there are some other costs, right? In a solar park of say 1 kilometer by 1 kilometer, there's 11 tons of silver. If you take a Tesla car, the electric car requires 6 times as many critical raw materials as an internal combustion engine, mainly for the battery. Okay? So we had to mine lots of materials to avoid CO2 emission. Okay, and let's look at that now. Okay, so electric vehicles. We think that's going to be the savior of the planet because of reducing CO2. But you see the costs. Copper, cobalt, lithium, nickel, and that's in megatons, right? Metric tons, 1,000 metric tons, thousands of metric tons. You can see the numbers are very large, okay? By 2040. Just for the electricity networks, the amount of copper that is required. Okay? And for low emission power generation, which includes power, photovoltaics, heat, thermal, bio, geothermal, we need resources. These technologies are not coming out of thin air. So we may be reducing CO2, but what are we doing? We're digging the planet even at a faster rate. We'll talk about hydrogen in a minute. And this is the shape of, this is the cost of copper. This is the largest copper mine in Chile, one of the largest. 2% of the world's supply comes from that. The digging holes in the ground. And how about cobalt for your batteries, electric car batteries? Where does that come from? Well, this is cobalt mining in the Congo. The people at the bottom of the pyramid supporting electric vehicles and this great green technologies are these people. So we have to ask the question, is this all sustainable? Look at hydrogen. You may think hydrogen is a solution, but it too requires platinum and ruthenium or iridium, which are noble metals, for the catalyst. So if you grow hydrogen, you still need to mine these very precious metals, and there are very little in supply for the catalyst, okay? And also, then again, for the fuel cell by which you will draw electricity. So even if you use solar and generate hydrogen, you still, it may be better, but you still need these resources. And that's the Toyota Mirai, which is the hydrogen car, which Toyota have placed a lot of emphasis that they're going around hydrogen vehicles rather than battery vehicles. But they too, still require 40 grams of platinum, which is a very valuable material in the cars. So I think what I want to say is we try to balance the planet in one way, by reducing CO2, but there's no zero cost route to that. The alternative technologies we are implementing may have a very large cost in terms of environment and the Earth's resources as well. Okay, so can we balance the planet? And what I want to say is that solar PV is one of the least impactful generating technologies because it uses one of the most earth-abundant materials, which is sand. It can, after 25 to 30 years, nearly the entire solar panel can be recycled. Okay? It doesn't stop us having to get more resources, but it is amenable to recycling. The silicon itself can generate for another 25, 30 years with refurbishment. The land area covered by photovoltaics cannot be utilized for other purposes like the Tibetan plain or mountain terrain or large water surfaces or desert. Large-scale pumped hydro rather than batteries may be the best technology for energy storage with solar PV. That is, you pump water up to a high level and you let the water run down again through a generator. So it's a solar hydro hybrid for energy. And hydrogen generation through electrolysis using PV may be the lowest cost in terms of resources for transport. And so with that, I will remind you that that's the energy source. And there is another technology which may come about, which is fusion. So if you can do fusion energy from water, that would be recreating the sun on Earth in a controlled manner. That may be the ultimate closing of the circle. Okay, thank you very much.
好我们非常感谢这个葛汉教授给我们奉献了一个精彩的一个演讲。接下来呢，我们也是很好的一个机会啊，我们可以向葛汉教授请教几个问题啊。好，这个还有其他。
So Professor Gehsn, nice presentation.
Thank you.
So you talk about the building of these mechanisms to generate CO2, right? So your talk is qualitatively, speaking, there's a balance, right? Maybe this generates more CO2 than the saving of by using the sun, right? So my question to you is, let's say example Tesla, right? Tesla, when you're driving, of course, you're not generating too much CO2, but when you're building the battery, so do we have any study like during the last 5 years, building these batteries versus generating CO2, are they really reducing CO2?
Yeah, that's a good question. And that's a question that is being increasingly asked. I think the projection from Tesla, it depends on how you do the numbers and calculate. So Tesla will say that if that car runs for, say, 10 to 15 years, then it will have saved or maybe twice the amount of embedded CO2 that is in the car. So it will say, if it runs for 5 years, it has recovered or saved the CO2 that has gone into the car, runs for another 5 years, and then it's generated positively. That's what they'll say. And I think that's correct. So my point is that I think we can most probably adopt technologies to reduce CO2, but that will require us to dig more and more. If we want more and more electric cars, right? So, and that's the point. I think it's very difficult to square the circle to say that there's going to be economic growth, population growth, and everything will be in balance. I think that's the question that I want to bring across.
Good afternoon, Professor. And I have a question about the TOPCon solar cells structure. Yeah, and I noticed that there is a ultra thin silicon dioxide layer, and like 2 nanometers. And how can we deposit such a uniform and ultra thin layer?
Yeah, I don't know, but all I know is it seems possible because a 620 watt solar panel has been, they're being sold now by Jinko Solar, right?
Yeah.
So I think that is what they've mastered industrially. It's as difficult, I would say, as making, say 5 nanometer CMOS.
Yeah.
But they've made 2 nanometer uniform oxide layer over 8 inches. So I don't know. It's process control. I think, yeah. So I think that's a big step in terms of solar photovoltaic processing,
so
which
maybe
has been mastered by a Chinese company, Jinko Solar.
Yeah, so maybe that's a commercial secret. Yeah.
Yes, it's commercial secret, obviously. Yeah.
Oh, okay. Thank you. Thank you.
Thank
you. Good afternoon, Professor. Thanks for your presentation. I'd like to ask that we know there are many kinds of solar cells, like the silicon-based solar cell or organic and others. What kind of solar cell do you think will be the mainstream for the balance in the technology to balance the planet?
Yeah, that's a very good question. Of course, I've only spoken about mainly silicon because that is 95% of the installed capacity now. It's still single junction, and there's an efficiency limitation, as I said, to about 27, 28%. Now, there are 2 ways you can go. Silicon is an inorganic material, and the energy that it is handling in terms of the intensity of the sun is very light for it. Okay, so it's 100 milliamps per centimeter squared is nothing for silicon. It can take 100 amps per centimeter squared. So the technology is going to become, or what is emerging is what they call concentrated solar. So if you concentrate the solar, you can have less material and generate as much energy. At that point, and you will see this being developed, you can go to other materials such as the 3.5s or quantum well solar cells, multi-junction solar cells in 3.5, and those have been shown under concentration to yield or give efficiencies approaching 50%. Okay, so that's one way is you concentrate the light, use less material, and then you can use very sophisticated Gen 3, Gen 4 quantum well type solar cells. That's one way to go. The other thin film way, the 5% of the capacity is what we call cadmium telluride from First Solar, but that, is cadmium and telluride. It's not going to really grow. Okay. Now, organics and what they call perovskites, there's a lot of excitement. I also work on organics. It's not going to be for terrestrial power generation, but it will be for light harvesting. So in this environment, silicon is no good. At 1/10 of a sun, organics and perovskites are much more efficient than silicon, which is an indirect bandgap semiconductor. So there will be new uses for photovoltaic conversion, but not necessarily for generating power into the grid. And I think for those technologies, the ideal materials are organics, perovskites, and low-cost solution processed photovoltaics. So those are the two extremes, I think. Very low intensity light and very high intensity light through concentrators, which will mean that there will be new opportunities for new material.
Thank you. Thank you.